Hello, everybody. Here's our second little pre-recorded video lesson here, having to do with impulse and momentum. In this particular one, we're going to look more specifically at collisions and what happens when two things start to transfer momentum to one another when they come into contact with one another. There's a lot of different things that are considered to be collisions. Obviously, there's the kind of the obvious things like we think about with sports collisions, but collisions can also be fall into any sort of a set of events where two objects with mass interact with one another and change their velocities as a result of that. They could either start at rest and then end up moving as a result, or it could be the opposite, where they're moving to begin with and then they come to a halt afterwards, something along those lines. But any sort of thing where two things are interacting with one another. And changing their motion as a result of it. So, like, for example, the dude on the paddleboard in the middle picture here, we wouldn't necessarily think of that as being a collision specifically, but this does have to do with momentum. The fact that if you've ever watched someone try to learn how to paddleboard before, that as soon as you start to move one direction, man, that paddleboard starts to move the opposite way. And the interactions between the two do function in a very predictable fashion, where I said one thing is moving one direction and the board's moving the other direction, and hilarity ensues. Lots of fail videos, by the way, fall directly into this category of momentum and collision. So, with this one, a couple of key things to keep in mind is that number one, whenever two things come into contact with one another and motion changes, the number one, momentum is being transferred. There was an initial situation, there was the interaction itself, and then there's the after situation. And then between those three things, we're looking at a transfer of momentum. That we had two objects with mass beginning wise. There was a set of velocities that was associated with what they were doing beforehand, and then somehow that velocity, that energy, got transferred to the after situation. Sometimes it's all of the momentum is transferred to one thing. Sometimes it's shared between the two things. Lots of different things can happen between this, but again, momentum is being transferred. And again, I mentioned this in the other one. Units of this, I'll remind you that momentum is kind of it's a dumb unit. I'm sorry about this. I don't like it. If momentum is mass times velocity, the units of momentum are going to be the units of mass times the units of velocity. So mass is in kilograms, velocity is in meters per second. Therefore, our momentum is in kilogram meters per second. It's a really weird thing. If you think about it in terms of impulse, sometimes it's also occasionally referred to as a Newton second, which is just another weird thing. But anyway, it's kilogram meters per second are the standard units that we're going to be using with this. So momentum gets transferred. The mass itself generally does not get transferred, but the meters per second do, depending on who's moving and what direction. The key thing here is that in the systems that we're going to be using here in our spherical chicken worlds, we're going to assume that momentum is conserved in a way that we can see it. Now, momentum is always conserved. Total momentum is conserved every single time. However, sometimes those forms of momentum are less visible than other forms, and I'll mention what I mean by this in a second. So this is the assuming assuming a perfectly elastic collision. Elastic collisions are like billiard ball collisions, where you have two things come together, they hit, and then they bounce off. There's not really a lot of the word they use is deformation. The balls themselves don't like smush and stick together. We're not really going to talk about the fact that some of the energy is lost in the collision when the two balls kind of smush. Like, imagine two Nerf balls hitting one another. There's a lot of squishing that happens before they bounce off. Think about it as two billiard balls where they're both, they don't really squish in the process. They literally just hit one another and kind of leave. When we talk about, like, say, for example, cars colliding with one another, we can assume a perfectly elastic collision, again, spherical chicken assumption, but we know that those two cars aren't truly bouncing off of one another. There's a lot of screeching of metal, there's a lot of bending of bumpers, there's lots of vibration, there's lots of turning this energy into not momentum, not velocity, turning it into things like vibration, sound, heat, other sorts of non-mechanical forms of motion that we don't see. So again, what we are going to do here is we're going to do a lot of this assuming a perfectly elastic collision where the things are literally bouncing off one another. Again, we know that this isn't really true, but we're going to take that as our as our story problem for this, our spherical chicken assumption. So again, we're going to think about collisions in terms of before, an instant of collision, and then an after. So it's important to make sure that you're thinking about what's happening in this conservation of momentum. So here's kind of what this typically looks like when we start to kind of turn into more of a math problem. So we've got, a truck and a car kind of coming in to hit one another. You've got to kind of think about the before situation and the after situation. So before, we've got the situation that's kind of up here at the left here, where we've got PAI and PBI. What in the hell does P mean? Remember that P is the letter that we use for momentum. A would be like object A, and B would be like object B. AI means the initial momentum of this particular object, and PBI means the initial momentum of this object. So if you want to kind of think about it, this would be object A, and this would be object B. I'm going to move this out of the way. You get here. Give me my pen. So this would be A. Come here. A, and then this would be B. And these would be I's because we're talking about before the collision. And then afterwards, we've got the similar sorts of things. We've got object A and object B, and then these would be now the final, or the after the collision was occurred. So that's kind of what we've got going up in this top equation. The momentum of the things on the left and the momentum of the things on the right. So the total momentum before the collision and the total momentum after the collision have to be equal. Now, this is not any one particular thing, but this is the total situation. So in this particular case, momentum is getting transferred. If you take a look at what's happening here the truck is moving and the car is not. So the car has zero initial momentum. The truck has all of the initial momentum. It's got a pretty decent mass, 3,000 kilograms, and it's going at 10 meters per second. So it's got all the momentum. And then BI here, the initial momentum of the car is zero. And then afterwards now, they're both sort of moving some direction. We don't know necessarily which way. So that original momentum that was contained just in the truck has now been transferred between now the truck and the car. So now we've got the total momentum between the two of them. We can kind of figure out what that is. So we kind of start plugging in our variables to this. So we would take a look at the momentum of the truck is the mass times the velocity of the truck. The initial momentum of the car is the mass times the velocity of the car. And then afterwards, we can look at the mass times the velocity of the truck after and the mass times the velocity of the car after. And this is really just math, plug and play. It's actually not that difficult once you start to realize kind of the before versus after. And that's the key part with this. So what do we got going on here? With our truck, we've got basically 3,000 kilograms times 10 meters per second. And then for the car, we had 1,000. Come on. Hold on. Give me my pen. 1,000. Come on. I'm going to have a hard time writing over this. 0, 0, 0 times 0. Again, our initial velocity here is 0 because the car itself isn't moving. And then afterwards, well, the mass of the truck is still the same. It's still 3,000. But now we want to know kind of how it's moving. That's the question that this one's asking for. What's the final velocity of the truck? And then for the car, it's 1,000. And now it is moving forward at 15 meters per second. Boop! It's kind of yeeting out of there. So what do we got? Well, this thing here adds up to 0. So our total initial momentum is going to be 3,000 times 10, which is, to get it in my calculator, our before momentum is 30,000. 31, 2, 3 was our total initial momentum. Final momentum, what do we have? Well, this is still going to be 3,000 times VF. We don't know what its final velocity. And then this part over here, 1,000 times 15, if I get a 0 off of there, is 15,000. Well, that would be obvious. Plus 15,000. There we go. And now it's just a matter of algebra. 3,000 times VF is equal to, I'm going to move this 15,000 over, subtract both sides. This is now going to be 15,000. 30,000 minus 15,000 is 15,000. And then I just solve. Divide both sides by that 3,000. I know the answer to this. Why am I doing this? 5 would be our answer. Meter per second. Okay. So here's what this means. Signs are kind of important here. I'll talk about this in a second. This is still positive 5, which means it's still moving this direction at 5 meters per second. It started at 10 meters per second. It's now going at 5 meters per second when it's done. And the little car is just shooting out of there at 15 meters per second. So these are both going that direction, meters per second. And so again, both of these are going out that way. Most of that speed now is being transferred to the car. The truck is still moving a little bit. So again, our total momentum is the same. Momentum on the left equals momentum on the right. But that momentum has been transferred and sort of rearranged between the two objects. It was at the beginning of this particular situation, all the momentum was in the truck. And now after the collision, there's some of the momentum in the truck and then some of the momentum in the car. In this case, it's half and half. It doesn't necessarily have to be that way. It just depends on the cases. So a couple of things to know about these sorts of problems. A key thing about this is you've got to really, really, really strongly pay attention to velocity. Not just the number, but the sign of the velocity makes a huge difference here, because changing momentum if things are not changing direction is very different than if they, switch and go the opposite way. So it's really important if you think about a case like A here, where this one has 0 initial velocity and this one has positive initial velocity. Then during the collision, something happens. Well, what can happen afterwards? Well, in this particular case, this is kind of like a billiards ball problem, where in this case, this one has 0 momentum, and this one now has all of the velocity. And in this case, it's going that same initial direction. I know it's kind of opposite the way I'm pointing on my screen, but it's going the same direction afterwards in the positive direction. So we would give that a positive sign. So if this started at 5 meters per second, then this one would maybe be ending at 5 meters per second, but going the same direction. If you take a look in case B now, there's a little bit of a different case here. Both of these things are moving. Let's say this one's moving at 5 and this one's moving at 5. The key thing here is that they're moving opposite to one another. So this orange one is maybe moving at plus 5 meters per second. It's really important to make sure that you give the other one a negative 5 meters per second, because again, they're moving opposite directions. And yes, it really does matter, because you guys know that two things hitting at 5 meters and 5 meters is essentially a collision, like in this middle picture, of about like a 10 meter per second kind of collision. So you've got to make sure that you've got those signs. And now afterwards, when we're taking a look at our final velocities, now this one has changed directions, and maybe now it's going, I don't know, some sort of negative VF. I don't know what that is, but it's going the opposite direction that it originally did. And now this one's got a positive VF afterwards, because it's changed direction. The white ball started at -5, and now afterwards it's going like +5 or positive whatever that number is. But you got to have the change in sign that's in there. It's really important. These two down here, we've got both of them going the same direction. Maybe this one's going at 5 meters per second, and this one's only going at 2 meters per second. Again, they're both positive because I can see the little blue arrows. This one's a bigger arrow, and this one's a smaller arrow, so I gave it a smaller speed. Now, when these guys hit, it's like a rear end collision. It's not nearly as bad. And so again, with these, you're going to get a change. Again, both of these would be positive. Maybe this one's leaving at +2. This one's also positive, but it's kind of going faster now. It's increased its speed, and maybe that's also positive, but a bigger number. So really important to make sure that when you're reading these story problems, you got to take that second and look at the signs. It's the most common mistake that students make. The math here is not hard. This is multiplying in algebra, but students forget all the time to change the value or assign numbers, positive and negative signs, to the velocity. So really important. Okay, the rest of this, I believe, is some examples of some of these kinds of problems that we've got going on. So some of these special cases of dealing with this. This is the classic octopus and hockey puck problem. I didn't make this one up. You can tell I just copied this out of a book, but this one is just like, it's one of those like, what kind of problems anyway? So one of the cases that you can do for a momentum problem is what we call inelastic collisions. Elastic collisions are where they bounce off like billiard balls, or like a baseball bat and a baseball is an elastic collision, or like you can think about two cars bouncing off one another being an elastic collision. Stick and slide problems are actually what we call inelastic collisions. A lot of football tackles are inelastic collisions. It's where one dude tackles and grabs the other, and they both kind of continue as a single object. That's what we would call an inelastic collision. So this is a really bizarre little example of a fake. It's not a real octopus. You can read the problem. There's an octopus thrown on the ice. Hockey puck hits it, and then how do we solve for the final velocity of the glob of octopus and puck when it's done? So with doing these, this is simply an M1V1, or this is simply a conservation of momentum problem. These are all conservation of momentum problems, but they all kind of take the same thing. MV and MV is going to be MV and MV. Okay, so what am I writing here? Well, this would be like the octopus, and this would be the puck. And this would be the octopus, and then this would be the puck. One of them is before the collision, and then one of them is after the collision. You just plug in your numbers for what they are. So we've got a hockey puck that's moving at 35 meters per second, and it strikes a rubber octopus. gross, that's thrown on the ice. We're going to assume that it's just sort of sitting there on the ice at the first. So our octopus is going to be 0.265 kilograms, and it has an initial velocity of 0. It's just sitting on the ice. Our hockey puck has a mass of 0.115, and it had an initial velocity of 35 meters per second. Now afterwards, octopus has a mass of this. Find the puck and the octopus slide off together. So here's what you can do with these guys. What I like to do when I write these inelastic collisions, rather than having V and V here, I know that these two V's are going to be the same because they're sliding off as a single, they're sliding off together. So there's a single velocity for the two of these. So what I like to write this as is the mass of the octopus and the mass, of the puck, and they're going to slide off together at the final velocity, whatever that is. And that's what I'm trying to solve for. I know what the mass of my octopus and the mass of my puck are. So this is 0.265 and 0.115 times our final velocity, whatever that is. So again, in this particular case, I know that because this is an inelastic collision, this is a stick and slide problem, these two things have the same final velocity. So you can either leave it as algebra like it's originally shown here, or you can kind of do their combined mass has a single velocity, whatever works for you. And at this point in time, it's actually pretty just math. So 0.115 times 35. Our initial momentum of our octopus was 0, so we don't really have to do with this too much of this. Our initial momentum of our hockey puck was 4.025. That is from these two things multiplied together. And again, this is kilograms, meters per second is the units of momentum. Awkward. And so I know 0.4025 is going to be equal to 0.265 plus 0.115, our combined mass of our two critters kind of stuck together. So this is 0.38 times VF. And then I just solve for VF, 4.025 divided by 0.38. And I get a final velocity of 10.59 something or other and change. This would be meters per second. Sig figs looks like I have 3, so let's call it 10.6 meters per second. Now, does this make sense? If I've got my initial octopus is just sitting there, this thing was going pretty fast. It was going at some speed like 35 meters per second, 35 meters per second. Does it make sense that they're both going to be moving in the positive direction afterwards? Yeah, because they're going to kind of slide together. So it makes sense that this is also a positive velocity. And then does it make sense that our velocity is a little bit slower? Well, yeah, because that hockey puck isn't very big. It's going pretty quick, but it's not very big. And so it hits that octopus, and the two of them together are quite a bit heavier. So they're going to be going kind of slow when they collide together. So kind of makes sense to me to see how those two work together. All right, a second set of problems that goes along with these is an uncollision, which is what we would call recoil problems. Again, it's if elastic or inelastic collisions are stick and slides, recoil problems are the opposite. It's usually a throw and roll kind of a problem here, where you're throwing something one direction, and because of that, you kind of end up moving the opposite direction. You see a lot of space problems, like there's a dude, like an astronaut floating out there, and he throws his air tank one direction, he's going to float back the other way. Or like the super contrived kid on a skateboard with a bowling ball because, physics. But in either case with these, if this is before and this is after, the solution is still the same when you think about kind of how these are working. It's like the opposite of an inelastic collision. The key point here is if you think about what's going on here, we've got the mass of the boy, and then you've got the mass of the... Sorry, I gotta erase this. You got the mass of the ball that's in here. Okay, so mass of the boy times the velocity of the boy. It should be times. Sorry, guys. Times velocity of the boy, and this is going to be the mass of the ball, B-A-L-L, times the velocity of the ball, B-A-L-L. Well, what was the initial velocity of these guys? Generally, in these kinds of problems, the initial velocity is 0. Works out pretty good. Usually they're holding still in one spot, and then you're going to throw. And if I'm the kid on the skateboard, if I throw that bowling ball forward, I'm going to be rolling backwards, and I'm going to get further away. So what we're going to get here when we're done is that we're going to have two different velocities. And again, this is where the signs become really important. This is going to be the final velocity of the ball. If this thing is moving forwards, then the final velocity of the boy is moving backwards. And that's going to be the same thing is true of our astronaut particular problem right here, depending on what we've going on. The VI of all of these problems is usually equal to 0. Our initial momentum is 0. So our final momentum is going to be mv times mv, and these guys are going to have to add up to 0. The big thing here that makes this really interesting is that one of our velocities is positive and one of our velocities ends up being negative. And that's really the key point with doing these. The combined momentum ends up being 0. So what happens is because you've got two different masses, that the momentum happens to be equal and opposite by the time you're done. So the difference in speeds is related to your difference in mass. You can see it in the two arrows here. It's a little bit easier to tell. This is a bigger object, so it's going to have a smaller mass. This is a smaller object. It's going to have a bigger mass to it because the total momentum of the two, in this case, has to add up to 0. The total momentum of the two objects is equal and opposite to each other. Here's an example of one of these recoil kind of problems, which is applied towards recoil of, say, the firing of a gun is a really common thing. When you're shooting a little tiny bullet out, how do you get that kickback to it? And again, this is related to conservation of momentum. So before you're shooting at rest, the momentum of the gun and the momentum of the bullet are both equal to 0. That's what you start off with. And then afterwards, you've got momentum of the gun, and then you've got the momentum of the bullet to it. So the momentum of the gun is going to have to be mass times the velocity of the gun, and then you've got the mass and velocity of the bullet. So again, why is it 0? Because our initial one to start was equal to 0. Our final two are going to have to add up to 0 or be equal and opposite to each other. So for the gun, and then we've got the bullet. There we go. Between the two of them, we've got a bullet whose mass is 50 grams. So we know it's 50.0 grams. I'm going to have to turn that to kilograms because it's in grams right now. So 50.050 kilograms is fired horizontally with a speed of 1,100 meters per second, 1100. And then I know what my gun weighs, because it says right here in my problem, 6 kilograms. And I want to know what my VF of the gun is. I don't know what it is. And again, these equal to 0 because, again, at the beginning of this situation, our initial momentum was equal to 0. So that means our combined final momenta have to add up to 0. So negative 6 VF equals 1100 times 0.05, 55 equals 55. Pardon me, sorry. Again, 0.050 times 1100. Again, I had to turn this into kilograms because our standard units of mass in any of these problems is going to be kilograms, so watch out for that. VF has to be equal to 55 divided by 6, right? Equals negative 9.1666. Which basically was negative 9.2. This would be in meters per second. It is meaningful that this is a negative number because remember, again, the bullet is moving that direction at 1100. That's a positive velocity. The gun's going to be moving the opposite direction, and it's a lot heavier, so it's going to have a much smaller speed. Again, that's why it's negative 9.2, the opposite direction. So don't forget your negative signs. It's a key point. I think that's it for today. Yep. So there we go. In terms of dealing with collision problems, again, total momentum is conserved. M1, mass times velocity plus mass times velocity, whatever you had at the beginning, equals your mass times velocity and your mass times velocity at the end. Keep in mind your units. Make sure that you're always in kilograms. Be very careful about dealing with positive and negative signs of your velocities, that if they're going opposite directions, you have to assign that negative sign. That's a really important part. The algebra itself is actually pretty straightforward as long as you pay attention to your signs. So again, these collision problems are always about conservation of momentum. Initial momentum equals final total momentum. So there you go. Have fun with doing these. Lots of really weird, dumb stories. You know, physics people, they got to come up with something, right? All right. Have a good one. Spread kindness, not corona, right? See you guys.